So in this video, we're going to be looking at series, and really it's going to be an introduction to quite a bit of new notation. And we're really looking to answer the question of what happens if we take an infinite sequence or an infinite collection of numbers and we add them all together. Okay, we want to see what happens to this infinitely long sum. So before we can look at the infinite long sum, let's take a look at just the finite sum. So first off, if I take some terms and I'm going to add them up, starting off with the first term and ending here, let's say, with the capital Nth term, and these are the terms being added up, what does my summation look like? So first off, this here at the bottom, that small n, that's my counter. So it starts off at 1. My first term is A1. My second term will be A2. My third term is A3. And I'm going to keep doing this until I get to this value of capital N. So the very last term in this summation will be A sub capital N. So that's fine. This is a finite summation. Okay, we are adding up n terms and seeing what we get. But this is not what we want when we're looking at an infinite series, when we're looking at adding up an infinite collection of numbers. Okay, instead, what we would like to do with this summation is we would like to do the limit as the number of terms in this summation approaches positive infinity. Okay, so we know how to deal with the finite sum, and then we know how to do limits. We can put the two together. Okay, so here we have our finite sum with our limit on the left, and then on the right, what we have now is an infinite summation. We have A1 plus A2 plus A3, except that this summation does not ever end. Okay, so here I'm just going to put that dot dot dot. There's no stopping at A sub n. This summation does not end. Okay, and so we actually have a better notation. Rather than using the limit as capital N goes to infinity of the finite sum, what we're going to do on the left-hand side is we're going to use the sum starting off at 1, and then we would say that our summation just goes to infinity. Okay, our counter never stops growing. So really what it looks like is, again, A1 plus A2 plus A3, our infinitely long summation, and this is how we're going to be representing it. It's the sum starting at 1 and never ending. Okay, so let's take a look at a specific example then. And this example we're going to spend a little bit of time going through. So it's the sum, again, starting at 1, going all the way to infinity. And we're looking at adding up the terms defined by 1 over 2 to the power of n. So here, our first term, if n is equal to positive 1, our first term is just going to be 1 over 2 to the power of 1. It'll be 1/2. Plus it's going to be, the second term is 1 over 2 squared is 1 over 4. And then we have 1 over 2 cubed is 1 over 8. And we have 1 over 16, 1 over 32. And again, we're looking at here the infinitely long summation. We're looking at the series. So this series is never going to end. Okay, so we can put that dot dot dot. This is our first series. So now what we're going to do is we're going to look at this series, and we want to answer a few questions. Specifically, we want to know what happens to this series if we continue adding up these terms forever. All of these individual terms are positive. So if I add up an infinite number of positive terms, does the actual result of this summation continue to grow without bound? Or does it approach some specific number? We're going to look at this series in a few different ways, but the first way that I want to examine it is just intuitively. If I look at adding up all of these terms, 1/2 plus 1 over 4 plus 1 over 8, what's going to happen to this summation? So if I look at just sort of a real number line, okay, let's start off here at 0, and let's put our number line over here ending at 1. Okay, then if I look at a distance of 1/2, that's going to be 1/2 of the way from 0 all the way to 1. So that's going to look something like this. Okay, to travel from here to here, that is a distance of 1/2. And then I'm going to look at this 1 over 4 again as distance. But 1 over 4 specifically will be 1/2 of the distance from here at 1/2 to here at 1. So that's going to be something like this. If this is 1 over 4, then now let's look at adding in 1 over 8, and that will again be half of the remaining distance. So this is going to be 1 over 8. And then we take our 1 over 16, and 1 over 16 will be again half of the remaining distance. And now let's sort of zoom in on what's going to happen here in the long term. Okay, it's going to get a little bit tight, but if I have taken now 1 over 16, the next term would be 1 over 32, and 1 over 32 is going to be the distance from here to here. And then we have the next term would be 1 over 64, and that's going to be the distance from here to here. And can we keep doing this forever? What's going to happen with this pattern as the number of terms goes to infinity? Well, each time we do it, we are simply taking 1/2 of the remaining distance, and so we will never actually end up passing this point with a total distance of 1. And so this is very much saying that if I take all of these values, 1/2 plus 1 over 4 plus 1 over 8 plus 1 over 16, and I keep doing this forever, that this summation is going to not continue to grow. Okay, it's not going to increase without bound. What it's going to do is that this summation is going to get infinitely close to the total value of 1. So if we look at this infinite series then, the sum starting at 1 and going to infinity of 1 over 2 to the power of n, we know 1/2 plus 1 over 4 plus 1 over 8 plus 1 over 16 and so on. If we continue this pattern forever, adding up this infinitely long collection of numbers, we don't get that this number increases without bound. Even though each of these terms is individually positive and we add up an infinite number of them, the actual total sum of everything altogether does not increase without bound. In fact, it just gets infinitely close to the value of 1. Now, I think this sort of visual interpretation of series is quite interesting, so I'm going to do this one more time again with the series 1 over 2 to the n. Let's take a look at another way to convince ourselves that the series summation actually just approaches 1, that it does not increase without bound. So here, let's take a 1 by 1 square. So if I assume that our base width is 1 and our height is also going to be 1, then the total area of this square is going to be 1 times 1. It's going to be just 1 unit. Okay, so fine. Now what does this have to do with the series 1 over 2 to the power of n? Well, let's look at this one in terms of area, okay, instead of in terms of distance like we did in the last one. So if I'm going to look at 1/2 of the area, that means I'm going to essentially be taking away and removing this portion. Okay, that portion there, the red portion, has a area of 1/2. And now what I want to do is actually cut this region in half again, and let's remove that one, because that's going to have a total area of 1 over 4. Okay, so if I keep doing this, this first one had a total area of 1/2, this one had a total area of 1 over 4. Then I do it again, let's say we cut it right here. Now this one, I remove it, and it has a total area of 1 over 8. And then I can do it again. This one has a total area of 1 over 16. And I can cut it in half again. And I remove that. That's 1 over 32. And this is 1 over 64. And this is 1 over 128. And we can keep doing this forever. We can keep removing these. But you'll notice that we will never actually leave this square. In other words, the total area of what we're adding up is never going to exceed the total area of this square, which is simply 1. Okay, and so this is just sort of another way of looking at it, okay, understanding that the summation, if I'm adding up from 1 to infinity, 1 over 2 to the n, this never exceeds 1, and all that it does is get infinitely close to the value of 1. Now, let's look at this series one more time. We have the series 1 over 2 to the power of n, and we are adding it up from 1 to infinity, giving us 1/2 plus 1 over 4 plus 1 over 8. And we want to look at, why this series is equal to 1, but now let's do it in a more rigorous way, not in sort of a geometric way. So we know that when we're looking at these terms being added up, they really correspond to our sequence, our infinite collection of numbers, all described by just 1 over 2 to the power of n. So we can start off here with our set of numbers. We have 1 over 2 to the n, 1 over 2 is the first one, 1 over 4, 1 over 8, and 1 over 16. Okay, now this is just our collection of numbers. Okay, what we would like to do with the series is add up this infinite collection of numbers, and we want to know what happens with that infinitely long summation. Now, we've done this sort of thing in calculus before, where we've taken something that seems impossible, and in this case, the impossible is adding up an infinite number of terms. We have no way of feasibly doing that. But we've solved that problem of dealing with infinitely large terms or infinitely small terms by using limits. Okay, and we're going to do the same thing in this one. So what we want to do is, first off, figure out some way of approximating that infinitely long sum. Okay, once we have a way of approximating that sum, we will work on increasing the accuracy of our approximation. And then once we know how to systematically increase the accuracy of our approximation, we can use a limit to bridge the gap between our approximation and the exact value. Okay, so that's that same three-step process that we go through with all of our applications, going way back to just looking at Riemann sums. And so the first thing, if I wanted to approximate this, well, I could do a really, really poor approximation and say that I could approximate the infinitely long series by just using the very first term, and the very first term would be 1/2. And that's where these partial sums come in. Okay, what we're going to do is, and I'll define it more rigorously right after that, but let's say that S1, okay, this is the first partial sum. That's going to be the sum of just the first term in the actual series. It's just 1/2 itself. And then I'm going to look at S sub 2. S sub 2 is going to be the sum of the first two terms in the series. So I have 1/2 plus 1 over 4. And if I add those two together, I'm going to get 3 divided by 4. And now I want to look at S sub 3, and S sub 3 will be the sum of the first three terms. That's 1/2 plus 1 over 4 plus 1 over 8, and if I add these up, I'm going to get 7 divided by 8. Now, why are we doing this? Well, if I want to get an approximation to the infinitely long series, I could say, all right, I'm going to approximate it by using, maybe the sum of the first three terms or the sum of the first four terms, and that will give me a semi-decent approximation because all of the terms over here are going to be very small. However, it's still just an approximation, and we're not really interested in approximations. So we need to fix that. Let's do just one more here. Looking at S sub 4, this is going to be all the way adding in 1 over 16, and that's going to give us a total here for S sub 4 of 15 divided by 16. Okay, so we've looked at the first four partial sums, okay, and now we want to know how to bridge the gap between these partial sums and the infinitely long series. And this is not so hard to do. So what we have right now is that our infinite series, 1 over 2 to the power of n, can be approximated by using here the partial sum. So let's say I could approximate it by using S sub capital N, okay, where capital N is the number of terms that I'm adding up, okay, and that's my approximation. Now, the one thing that we also noticed is that intuitively, if I increase the number of terms being added up, if I were to add up 100 terms compared to adding up the first four terms, my approximation should be getting better and better. So if I increase the number of terms, the approximation gets better and better. And so if I take here the limit as n approaches infinity, and that's the limit as capital N approaches infinity, where capital N is going to be the number of terms in my partial sum, then that limit is going to be exactly equal to our infinite series. And this is very much what we're going to be using. Okay, and I'll do this in a formal definition in a moment, but if I want to deal with the actual infinite series, the infinite summation, then I can do that by looking instead at just the partial sums. Each one of these partial sums is just a finite, limited amount of terms, and we know how to deal with that. And then all I can do at the end is do the limit as the number of terms goes to infinity to bridge the gap between our approximations and the infinite series. So what does that mean for this particular series? Well, if I want to know here what my partial sums all look like, what I want to actually do is look for a pattern in these partial sums. So the first one is 1/2, and then 3 over 4, 7 over 8, 15 over 16. Then what would I get here as a pattern for the nth partial sum? So the first thing is this corresponds to n equal to 1, this one to n equal to 2, and so on. So let's try to figure out a pattern for the denominator, and then we can use that to find a pattern for the numerator. And in this case, you'll notice that my denominators are all just nicely the powers of 2. We have 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4. So my denominator can be described as 2 to the power of capital N. Now, if that's my denominator, then what's the numerator? So think for a second, what's the pattern here in the numerator? 1, 3, 7, and 15. It's a little bit weird, but try to see if you can come up with it. You will notice one way of describing the numerator is that it is simply equal to the denominator minus 1. So in other words, I can just do 2 to the power of capital N and subtract 1. And this formula right here describes all of my partial sums. If I want to know what's going to be the partial sum of the first 1,000 terms, well, the first 1,000 terms, if I were to add them up, would be 2 to the power of 1,000 minus 1 divided by 2 to the power of 1,000. Okay, so now that we have this nice formula to describe our partial sums for this series, let's actually go and do the limit of this partial sum as the number of terms goes to infinity and see what happens there. So we have now our infinite series, the summation of 1 over 2 to the power of n. If I want to know what that's equal to, I can do the limit as capital N goes to infinity of s sub capital N, which is just going to be the limit as n goes to infinity of 2 to the n minus 1 divided by 2 to the power of n. And so what happens here with this limit? Well, as capital N approaches infinity, unfortunately my denominator goes to infinity and my numerator goes to infinity. So what I have here is an indeterminate form, infinity divided by infinity. And so what can we do if we run into an indeterminate form like that? Well, one of the things that we can certainly do is just to use L'Hopital's rule. So here I can take the derivative of the numerator and the denominator separately from each other, and I end up with 2 to the n times ln of 2 in the denominator. And because here the derivative of minus 1 is going to be 0, I end up actually with the exact same derivative in the numerator. And so now, simplifying this, even though individually they go to infinity, simplifying it, I get that this limit is just going to be the limit of 1. It's just going to be 1. And so what we have here is now sort of a more systematic way of showing that this series, the sum of 1 over 2 to the power of n, does indeed simply approach the value of 1. It is equal to the power of 1. It does not grow without bound. So that worked out nicely, but what I want to really focus on now is the importance of these terms in the middle. Okay, these partial sums were really the tool that we used to bridge the gap, okay, between our collection of terms and the infinite summation, which was called the series. Okay, so let's actually go and define these partial sums, okay, and then let's formally sort of connect the idea of a partial sum and the infinite series. Now, this definition is going to seem sort of a little bit silly. We have a partial sum, and a partial sum is part of the infinitely long series. Okay, so this is what we saw before. It is really, if I look at the nth partial sum, the capital Nth partial sum, it's going to be the sum of the first capital N terms. So it's A1 plus A2 plus A3, all the way stopping over here at capital N. So first off, we get that this partial sum is the sum of the first N terms. So fine, we call this here the nth partial sum. And then what we noticed in the last example that we were working through together is that we can use here the partial sum as an approximation to the infinitely long series. And the more terms that we include in our partial sum, the more accurate the approximation gets. So the really important conclusion here, the connection we have between the partial sum and the infinitely long series, is that if I do the limit as the number of terms in my partial sums go to infinity, then this can give me the infinitely long series. It'll give me the value in the infinitely long series. Now, is this always true? Okay, we want to be a little bit more careful with the way that we talk about this connection, okay, the connection between the series and the partial sum. So now let's take a look at that connection. Here we have the definition, the connection between the nth partial sum and the actual complete sum of the series itself. So if we have that S sub n is the nth partial sum of the series, then first off, if the limit as the number of terms in that partial sum approaches infinity, if that limit exists, then we would say that the series is convergent, okay? Because the series will actually be equal to that number. So in the last one, we saw that this limit was equal to 1. And so we said that the actual series itself was just equal to 1. In that case, we say that it is convergent. Okay, and that's the same idea that we have of convergence for improper integrals, the same as we saw, or you can see for sequences. Okay, and in that case, if it's convergent, if that limit exists, then all three of these things are going to be equal. Okay, we have that the series is equal to that limit as n approaches infinity is equal to whatever value you get as your limit. Okay, now what if that limit doesn't exist? Okay, so if that limit doesn't exist, then we actually would say here that the series is divergent. Okay, and then again, that's very much in line. That's very much the same way that we defined divergence for improper integrals, okay, where the limit does not exist. So when I was saying in the last little section that we don't always have this case, or we have to be a little bit careful when we say that the limit of the partial sum is equal to the series, it's simply because this limit on the right-hand side here, this limit doesn't always exist. And if the limit doesn't exist, well, then these two things are not actually going to be equal to each other. Okay? But this is in general how we're going to define convergence and divergence of a series. We can define it in terms of their partial sums. If the limit of the partial sums exists, then the series is convergent, and if the limit does not exist, then the series is divergent. So going back to the series that we saw before, we could say that here our series 1 over 2 to the power of n, okay, was equal to the limit as n approaches infinity of S sub n, which turned out to just be the limit as n approaches infinity of 2 to the n minus 1 over 2 to the n, and this was just 1. So according to this definition, we would have that this series is convergent. Okay, and now what we're going to do in the next section is we're going to take a look at some specific special types of series. Okay, we're going to be looking at telescoping series, we're going to be looking at geometric series, and we're going to be looking finally at p-series. And for each one of them, we're going to be asking the same question. Does the series converge or does the series diverge? Okay, and very much we're going to be looking at these partial sums and asking ourselves if the limit of those partial sums exists or not.